A4 is called the binomial distribution, and it's pretty aptly named. It's when you take a binomial and raise it to various powers and see what happens. There's a lot of patterns that show up. We'll kind of scratch the surface of it, but you can really get deep into this stuff. And you'll see quite a bit of statistics, so it will have some roles there if you take that course. So if you're already in it, you probably will see some connections. So start off, let's do a couple things you should be familiar with. Expanding x plus y squared. Now remember, that means you need to FOIL x plus y. Of course, there are some shortcuts you can take. Basically, x times x happens, x times, outside, x times y, plus this other x times y. Now I'm going to keep those in alphabetical order so that I can tell those are like terms. And then plus y squared. So that's going to be x squared plus 2xy plus y squared. Pay close attention to the different combinations of things that happen. The x, y's, that happens twice. So that's the things we're going to focus on as we get deeper into this. Now, if you do x plus y cubed, you're going to take that result, x squared plus 2xy plus y squared, times one more x plus y. Now, I know that's true because this was already x plus y twice, and I want to multiply by x plus y one more time. And then that's the process. You can really only multiply two numbers together at a time. So in any of these problems, you multiply two terms by each other and then multiply by the next term and so on. So here we go. So x squared times x is x cubed. X squared times y is x squared y. 2xy times x is 2x squared y. Now what I like to do is kind of stack these things. So my problem's going to get a little more vertical, but I think it's easier in the end. All right, 2xy times y, so plus 2xy squared. Y squared times x is xy squared. And finally, y squared times y is y cubed. So I'm going to make it basically one big addition problem, put it all together. I'm going to get x cubed plus 3x squared y plus 3xy squared plus y cubed. So hopefully, just a review, should be fairly familiar. And we're going to start looking at the patterns we're seeing through the coefficients. Now look at what's going on with these coefficients. I'm going to do what's called Pascal's triangle. And you may have saw this at some point somewhere along the way, but if I just had plain old x, then its coefficient is 1x. Now if I have x plus y, we have 1x plus 1y. If I do x plus y squared, which I just did, you have 1x squared plus xy plus y squared. Again, I'm just looking at these coefficients right now. And what's going on is you're going to add whatever terms are here to kind of go down the triangle. That'll make more sense as we go. So let's do x plus y cubed, which we just did the old-fashioned way by hand. But what we saw was 1x cubed plus x squared, or 3x squared y plus 3xy squared plus y cubed. So again, to get more terms, you just keep the ones going out, and whatever's in here adds, and that creates the next term down. So the next row for x plus y to the fourth, I'll just reveal a couple more rows. The ones are going to come down. 1 plus 4, you'll have 4. Let's see, we'll have x to the fourth. We'll have 4x cubed y. We'll have 6 here. We'll have another 4. We'll have a 1. So that's what we ought to be seeing. And then if you do another row, 1's come out. So 1x to the fifth, 5x to the fourth y, 10x to the third y squared. The x's count down while the y's count up. And then another 10, and then a 5, and then 1. And that's the pattern. That'll keep going forever. You can keep using this as much as you need to. It's pretty good for powers under 10, I would say. Once you get up in the teens and beyond that, which we will explore a little bit, this gets pretty clumsy. It takes a long time to write it all out, especially if this comes up somewhere and you just need it to solve one problem. You're not doing the homework assignment, you can make this triangle and kind of use it over and over. But if this binomial distribution just pops up in a calculus problem one day, it's kind of good to have a shortcut to this. I do want to ask you this question. What does each row add up to? So let's go take a look at that. So we had 1, These add 2, those add 4. 1 plus 3 is 4, 7, 8, 5, 11, 15, 16. And if you're guessing that might be 32, let's find out. So 1, 6, 16, 26, 31, 32. And hopefully you're recognizing those are powers of 2. It's not by coincidence because this was x plus 1, 2 terms squared. Let's put it this way. This was only 1 term. This was 2 terms. 2 terms squared. So 2 times 2 is 4. If you look back what we did in the first example, there were 4 multiplications that happened. X plus y, 2 terms cubed. There were 8 multiplications that happened. And here's how they all played out. 1 here, 3 there, 3 there, 1 there. And that pattern is definitely going to hold. 2 terms to the 4th, that's 16 multiplications. That's 32 multiplications. So let's look at more of the details of what's actually going on here, exploring why this triangle is happening. I just talked about how x plus y cubed, there are 8 multiplications happening. Now we saw those when I first started. We did it the long way. We'll take another look at this. Now I'm going to do it kind of color-coded. So if you have trouble with colors, hopefully you kind of follow what I'm doing and where things are moving. So you got x plus y 3 times. What I did was I made each one a different color. The red group, blue group, green group. If I just FOIL, I get this red x times this blue x. This red x times the blue y. Red y times the blue x. Red y times yellow, or blue y. And then I'm going to multiply by the other x plus y. So by color coding this, hopefully you can see the specific combinations of x's and y's that create these terms. This is kind of like the distinguishable permutation idea that we did before. Another reason I like to do that lesson first. It's really similar to that because if this is all black and white, I can't tell this x squared y from this x squared y because they're all just x squared y's. But once I start color coding, you kind of see how they're uniquely made. This was made of a blue x and a green x. This was made of a red and a green x. So they're kind of, each one's got a unique makeup of x's and y's that creates it. It's like a signature. And now if you start thinking about how your 1x cubed, your 2x squared y, 3x squared y's, your 3x y squareds, your y cubed are made, well, to get x cubed, there's only one way to do that, and that's by taking all 3 of the x's purely and nothing else with it. To get the x squared y terms, so let's just kind of simplify that. Well, you had to do different combinations. In fact, and again, this is why I like to do the previous lesson first. You had to take every combination of 3 x's and how they could be combined in groups of 2. And that's what you're seeing. You can see blue and green. And you can see the blue and red, and then finally red and green. And you're going to see the same thing with the y's. To get y squared, you had 3 y's, and you're assembling them in groups of 2. You're looking at all the ways that can be done, and it's 3 ways. And what this is leading up to, because that's true, is combinations. So the next piece I'm going to show you formally is that we can use combinations to figure out these coefficients that should go with these. And again, the coefficients come from the fact that I have 3 x squared y terms. Let's just put a 3 right there. And I have 3 x y squared terms. Here they are. X with 2 y's, x with 2 y's, x with 2 y's. All right, let's try to put these ideas together and think about how we can make a shortcut with this. So each coefficient from Pascal's triangle, we can derive it from the combination formula. And I sit here to pay attention to the x's for each term. You can also use the y's. It really doesn't matter. I think it's kind of easy to just think about the x of the first variable you have here. So this one would be just plain x, so that's 1. This is just 1 and 1. So let's start with x plus y squared. So this first term would be comprised of both x's multiplied together. Of the 2 x's, you combine them both together. Of the 2, you pick 2. To get the term in the middle, there's only 1 x in it. It's 2xy. So you took the 2 different x's from multiplication, and you picked 1 each time. So of the 2, you chose 1. And then the last term was purely y squared. So of the two x's, you didn't use any of the x's because it was purely y. That's the idea we're going to use. So for x plus y cubed, since we've done that one several times, to get this first term, this x cubed term, of the three x's, you had to use all three. To get the next term, it was 3x squared y. Of the three x's, you used two of them. So 3 choose 2. The next term was 3xy squared. Of the three x's, you used one at a time. And then finally, the last term is purely y cubed, so it's of the three x's, you didn't use any of them. That's the easiest way I know to really explain that or think about how it works. All right, let's just practice these skills a little bit. So if we want to find the expansion of x plus y to the 6th power, well, my chart, my Pascal's triangle, I went up to 5 rows. So let's go back to that and fill in the 6th row. We should be able to get this pretty easy. So the ones come down, or add these together. So 15, 20, 15, 6, 1. So 1, 6, 15, 20, and then it counts back down. And then we just think about our x's. So the first term is all the x's multiplied together. The next term was 5 of the x's, 1 of the y's, and it had a 6 in front of it. Again, these are just coming from the Pascal's triangle. So the pattern's going on. Your x's are counting down 1 power at a time, while your y's are counting up 1 power at a time. When you get done, you'll have purely y to the 6 with no x's. So that's the other pattern going on. Now, if we thought about color coding all this, the way we did x plus y cubed, to get x to the 6th, of the 6 x's here, you had to use all 6. So that would be 6 choose 6, x to the 6th power. All right, you kind of have to know where it's going to head next. You're going to have x to the 5th y next. And to make that happen, of the 6 x's available, you're putting them together in combinations of 5 at a time. So there's where your 6 choose 5, x to the 5th y would come in. And then that's the way the pattern's going to continue. To get x to the 4th y squared, of the 6 x's, you're choosing 4 of those at a time. So 6 choose 4 next, and then so on. And if you get confused on whether to use the x or the y for your combination, it honestly doesn't matter. That symmetry that's happening in the Pascal's triangle, it lets you get by with whichever way you want to go. You could do this from the y perspective. 6 choose 0, 6 choose 1, 6 choose 2. It would be the same thing. That's fine. You can go either way you want. It's whatever your preference is. And then finally, just to illustrate that point, if you did it from the perspective of the y's, that's what it would look like for your combinations. You'll see some problems like this in the book where you're asking you to find a specific coefficient given a binomial here. So this is x plus y to the 15th. We're supposed to find the coefficient that would go in front of x to the 10th and y to the 5th. You could do 15 rows of Pascal's triangle. That's fine. I think the easiest thing to do is knowing that of the 15 x's available, you would be choosing 10. Or if you want to go the y route, of the 15 you choose 5, and you'll get the same thing either way. And just a quick reminder about how that works. The combination formula, it's the total number of things you have factorial over the things you're choosing times the number you're not choosing. If we chose 10 out of 15, that leaves 5 left over. And either way you go, it's the same formula. So because these two numbers have to add to that, and so do your coefficients, that's why it's going to check out either direction you go. Let's talk about how to put this in the calculator. So 15 choose 10. So first I'm going to do 15. I do my first number. Then I go to math. And then there's a probability menu, so we go over to that. And then here's your permutation and combination. And if you need factorial, it's on there as well. But we want combinations, so option 3. And I'm doing 15 choose 10 this time. I get 3003. And just to show this is okay too, I'm going to bring this down and do it with 5. Again, just to show you that that's okay and it's going to be the same thing. So it's 3003 either way we go. One last time, 15 choose 10 or 15 choose 5 is 3003. That's the coefficient you're going to have for C there. All right, problems like this will be the trickiest thing you encounter. And it's because we've got another coefficient that's already in here. So we've got to really be careful with our coefficients and the numbers we've already got going on. So before I do any kind of combination stuff, I'm going to think about, if I wrote this binomial out times itself 5 times, what are the pieces going to look like? So first up, I'm going to purely have 2a to the 5th power. The coefficient there is going to be 1 because that first coefficient is always 1. If you want to do a combination, you could say 5 choose 5. Of the 5 2a's, again, if you list down all 5 terms, I'm going to use all 5 of those. There's only one way to make that happen. All right, for the next one, of the 5, and again, you can think of it in the perspective of 2a, or for the number of 4's you're going to use. You're not using just purely x's and y's, but the pattern holds. So you've got to be careful with these numbers now. So of the 5 available, I'm going to use groups of 4 of those. And the combinations are just basically counting down each time as well. There's a lot of counting up, counting down kind of patterns going on here. All right, so next, so 5 choose 4. Of the 2a's, there's going to be that to the power of 4. And of the 4's, to the power of 1. And if I haven't pointed out already, the powers of your 2 terms always add up to that power. Always, no exceptions. So next would be, of the 5 2a's, choose 3 of them. So 2a cubed times 4 squared. Run out of room, so come down here. So of the 5 2a's, 5 4's, choosing 2 of the 2a's. So times 2a squared, because I'm just counting that down, times 4 cubed this time. 5 choose 1, 2a to the 1st, while 4 is to the 4th. It's counting up. And then 5 choose 0. There won't be a 2a in this problem. If you want to do 2a to the 0, you can. But you will have 4 to the 5th power. So I've showed you how to put these all in the calculator. So I'm going to go ahead and maybe do a few of these with you, but then sort of skip ahead. So 5 choose 5 is 1. So 1 times this term. We know 2 to the 5th is 32. And we know a to the 5th is a to the 5th. Okay. So 5 choose 4. 5 choose 4 is 5. If you can do the formula pretty quickly, you could probably come up with that. The next term is going to be 5 times 16a4 to the 4th times 4. So I'm going to actually come down and do kind of the final answer row. 5 times 16 is going to be 70. 5 times 16 is going to be 80 times another 4 will be 320. A to the 4th. What you're going to find is your a term, since a is really truly the only variable in here, you're going to see your a's counting down. A to the 5th, a to the 4th, a to the 3rd, and so on. The coefficients get kind of tricky here. Let's do one more, and then I'm going to just skip ahead to the answer. And if you have any questions about it, you can always ask me. I can maybe explain it in more detail if I need to. All right, so up to this term, 5 choose 3 is 10. So this is going to be 10 times 2 cubed, so 8, and then a cubed, times 4 squared, so 16. And that's going to be 1280 a cubed. So we'll go ahead and put all the rest of these in the calculator. Just be careful with your raising this number to the power, but then keep an a to that power as well. Okay, so once you have it all completed, to check your work here, 32 a to the 5th, plus 328 to the 4th, plus 1,280 a to the cubed, or a to the 3rd, plus 2,560 a squared, and then 2,560a, so those two have the same coefficient, plus 1,024.